But today I'll be talking about mostly Aluto volcano and yeah, the research that we have developed there. So first of all, thank you to Sasha for having invited me to present our research, and of course, big thanks to all the collaborators that have made all this research possible. So I'll start with a quick introduction or background in terms of volcanic hazard and volcanic risk in Ethiopia. So here we have the country of Ethiopia. All these triangles are hosting volcanoes. We have this line, which is basically the Ethiopian rift, so the northeasternmost branch of the East African rift. And then we have second main group of volcanoes around the Afar area, which is close to the triple junction between the Ethiopian rift, the Red Sea, and the Gulf of Aden rifts. And so, as you can see, there are many volcanoes in the country, and several of them marked by these pink and red colors have erupted recently. So the red color is eruptions since 1950. So many volcanoes, some of them erupting in recent times. So great volcanic hazard in general terms. And if we focus and we zoom in into the main Ethiopian rift, this is a preliminary pseudo-quantitative analysis made by Karen Fontaine, basically looking at the known frequency of eruption at different volcanic centers along the main Ethiopian rift, and also looking at whether the eruptions from those volcanic systems are predominantly explosive. And as you can see here, Aluto is going to be the focus for talk today, but so both Aluto and Corbeti have the highest known frequencies of eruption, and also their eruptions tend to be predominantly explosive. So if we move into the risk side of things, so in this case, analyzing the exposure around this volcano, this is a Corbeti caldera, you see that there are several areas around the volcano that are characterized by relatively high population densities. And the same occurs in the case of Aluto. If we zoom in here, we see that there is a significant amount of people that is living, but also working on and around Aluto. And this is Aluto's edifice built after the last caldera-forming eruptions. So this is the edifice that has been built as a result of these post-caldera eruptions. And we also have critical infrastructure, for instance, geothermal power plants here in the caldera floors center. So we need to take into account this, and we need to take into account the characteristics of rift volcanic systems in order to then quantify their hazard. So some of the things that we've learned from past research, including the recent RiftVolc project, is that eruptions of the systems in the main Ethiopian rift tend to be not very frequent, or less frequent than in other tectonic settings, such as subduction zones. And on average, and this varies from one volcanic system to the other, there's one every several hundred of years. Eruptions, as we've known recently, may be more explosive than we previously thought, and Aluto is one example of this. And also we've seen that vent opening patterns, either at silicic or basaltic volcanic systems, or related to basaltic or silicic eruptions, tend to have these complex vent opening patterns. So we need to account for that in our hazard assessments. And also importantly, data scarcity is still very significant in the area. So epistemic uncertainty related to lack or incomplete knowledge is really relevant, and we need to account for it when we do our hazard assessments. So one way of going through these characteristics and try to incorporate them into the hazard assessment is by using event trees, which first of all, there are conceptual models of the functioning of our volcanic system of interest. So we go from the left-hand side of, we start from general events, such as will the volcano erupt within a given time window, towards more specific events, such as from where eruptive activity may be sourced, or how big an eruption might be, and then into even more specific events, such as which hazardous phenomena may be generated and how far they may travel. And of course, there are not only conceptual models, but there are also quantitative models. So we'll be looking at ways of quantifying the probabilities in different nodes of the event trees as we go along the presentation. And I'll start with the probability of eruption size at Aluto. And here the problem, as with many volcanoes and in the main Ethiopian rift, but worldwide, is that what we would need to estimate our probability of eruption size would be records that are plentiful of eruptions, so we can estimate our probabilities using the data at our target volcano only. But the problem is that usually what we have is records that are characterized by very few eruptions, so we cannot estimate in a robust manner these probabilities. And so one possible solution is to try to fill in the gaps using data from analog volcanoes, or volcanoes that are similar enough to our target volcano as to borrow some data and information from these similar volcanoes. And that's what we did using this new method called volcano analog search, or volcans. And in general, along the presentation, I won't be talking in detail about all the methods, but I invite the attendees to check the references and see the methods. And I'm open to any questions or discussions about those methods offline, but also during the question time as well. But basically, we used global volcanological data sets and different volcanological criteria to try to understand which volcanoes were the most similar to Aluto volcano. And in this case, we're looking at the top 50 analog volcanoes to Aluto. And what we can do, given that we cannot derive this probability distribution of VI sizes from data from Aluto exclusively, we try to use these top 50 analog volcanoes to derive this probability distribution. And here, one problem is that there's a compromise between selecting too few analog volcanoes or too many analog volcanoes. And this is a source of epistemic uncertainty, because different sets of analogs will give rise to different estimates of these probabilities. And so we can try to incorporate that using our event trees. And here we're still looking at conditional probabilities of eruption size, but in this case, one single value will represent the aleatory uncertainty or natural variability of the system only. But given that we are trying to incorporate epistemic uncertainty, we have a distribution for these probabilities of eruption size. And another thing that we can do with event trees is then incorporate the long-term probability of eruption and go from conditional probabilities of eruption size into joint probabilities of eruptions occurrence and size. So here we are keeping the estimates for our epistemic uncertainty, but we are looking now at probabilities of different VI sizes in a given time window, in this case, 50 years. So these are the type of things that we can do with event trees. Then moving into pyroclastic density current hazard, one of the things that we need to take into account for PDC hazard is from where the activity may be sourced. So the probability of vent opening. Here we have a data set of past eruptive vents post-caldera at Aluto, and what we can do is to use a data-driven method to derive this probability of vent opening given eruption, which basically will give us high probabilities of vent opening close to areas where many past eruptive vents are located. And so we can incorporate this variability in vent opening and combine it with the variability in terms of the PDCs that may be generated at the system, and we base that on knowledge of past eruptions from field deposits. And we try to explore this variability in terms of column collapse height or PDC mobility, etc. And in this case, we used a very simple model, the energy cone, which allowed us to combine it with a relatively inefficient uncertainty quantification technique, which is Monte Carlo sampling. And by combining this variability in PDC phenomenology with the variability in vent opening, we can compute these probabilities of PDC arrival given eruption. This is a graded map approach, and what we found is that the highest probabilities of PDC arrival are located on the caldera floor, but also on the western and southeastern flanks. If we zoom in into another area and we adopt a different strategy to quantify uncertainty and assess PDC hazard, we move into a more point-wise analysis. We'll be looking at these points along the road on the caldera floor of Aluto. And what we do here is to use a more complex PDC model combined with a more efficient uncertainty quantification technique. So the idea here is to run a limited number of our PDC model, Titan 2D, in order to then construct or build a statistical model, which is the Gaussian process simulator, that can act as a surrogate or an approximation of the behavior of our PDC model. And so once we've built our custom process simulator, what we can do is to evaluate it. And here we wanted to look at PDC channelization processes. And so we limited our vent opening area to this sector over here, because we expect that those flows over here, given the topography, are going to be mainly channelized through this main valley over here and be conveyed towards the caldera floor. And so what we can do then is to have a look at the results in terms of the probability of PDC arrival given different values of vent radius or smaller. So in each of these points, we are considering emulator evaluations for vent radius equal or smaller than each of the values. And so when we look at the maximum value, we're looking at all our emulator evaluations. And what we can see is that the highest probability of PDC arrival occurs at the exit of this channel over here. And actually the next point has the second lowest probability of PDC arrival. And that hints us to the fact that flows struggle to propagate over this caldera, over this flat area, which is the caldera floor. And then we see on this point.
You have 10 minutes now.
10 minutes, okay, thank you very much. So on this point, beyond this topographic obstacle, we see that the probability of PDC arrival is quite low, is the lowest of the points that we have explored in this example. And then to finalize, I'll speak about a regional probabilistic volcanic hazard assessment of tephra fallout that we are currently carrying out. And again, what we want to do is basically we start from the point that we want to estimate the frequency magnitude relationships for all these many volcanoes in Ethiopia, 60 plus volcanic systems. And the way that we went through it was using expert elicitation, but the problem is that we cannot elicit 60 plus distributions from the experts. So what we did is to divide the volcanoes into two main areas, the Ethiopian Great Volcanoes and the Afar volcanoes, and ask the experts about different variables of interest for these two areas. And I'll give an example for the main Ethiopian rift. So we asked the expert to idealize example volcanoes. And so with this method, which is called the shelf method, one of the things that we want to achieve is to obtain a consensus distribution from all the experts. So a distribution that all the experts agree with. And in this case, main Ethiopian rift is the number of eruptions in 100,000 years, what we're looking for, and that's what we obtain from the experts. So we can use that as a starting point for our analysis, but then we can combine that information with other sources of information, the same as we were talking about Aluto using volcans. We can do it for the 60 plus volcanoes, and also in all the cases where we have volcano-specific data, we can incorporate that information, and all together, the idea is to develop and compute this regional multi-volcano tephra fallout hazard assessment. So it would be similar to the example here by Jenkins, but applied to Ethiopia. And just to conclude, what we've seen is that volcanic hazard assessment is very relevant in the main Ethiopian rift in Ethiopia, that we need to account for the particularities of rift volcanoes in order to compute our hazard. And also we need to incorporate the substantial epistemic uncertainty linked with the hazard. Then event trees can become very useful tools to quantify hazard and rift settings, and we've seen that they are both conceptual but also quantitative hazard models, and they may be portable to other volcanic systems beyond Aluto. We've also seen that pyroclastic density currents is very important at Aluto, and by exploring different strategies, we can obtain a comprehensive, broad view of PDC hazard at the system. And finally, we've seen that by combining expert elicitation and analog volcanoes, sets of analog volcanoes compute with volcans, these have been successful strategies to tackle data scarcity in the area from local up to regional levels. And I'll just leave here a list of references that have been included in the presentation, in case anyone wants to go and check them later on. And I think with that, I'll have finished. And yeah, thank you very much for everything. And I'm happy to take any comments or questions.
Excellent. Thanks, Pablo. That's an impressive breadth of methods that you presented in such a short time. Karen, you have a first question.
Yes, thank you, Pablo. Thanks for that brilliant presentation. I was wondering if you could comment on how the event tree that you have for Aluto, for example, it's obviously based on geological data, expert citations, analog volcanoes, etc. So it's mostly informing the longer term hazards, hazard assessment. So could it easily be adjusted to work in an operational setting during a volcanic crisis? So for example, if Aluto starts to show unrest tomorrow, could you easily adjust it?
Well, yeah, I mean, it would be a matter, so let's come back to the Aluto entry. So it would be, I think, mostly a matter of expanding this. Let's show the whole tree. It would be a matter of expanding this first area of the graph. Can you see my cursor, right?
Yeah.
So here we are trying to quantify the long-term probability of eruption, but probably one of the key aspects, if we are moving into the short term, would be to try to understand how we go into from the 50-year time window hazard assessment into the, say, month or several months or weeks. It depends on the data set that we would have available to quantify our probabilities, but it would be a matter of expanding this area of the event trees and incorporate whatever seismic data, deformation data, gas data that we may have to inform that short-term probability of eruption of the system.
Yeah, cool, thanks.
I would have a question that often comes up when it comes to hazards. It's about last mile. How do you make use of this information that you gathered, and how do you bring it to the people in the end?
You mean in conversations with the end users, you mean?
Mm-hmm.
Yeah, that's a very complicated issue. I suppose we would need to talk with in-country partners like Atala and Elias and Gesahang. But it's always a challenge, I guess, to convey the hazard assessments into the end users. But I think it's a matter of mutual trust between the end users and the developers of these methods, and then trying to see where these methods and results may be more useful for the end users, and then just trying to understand each other and see how that collaboration may work best. I think I don't have a unique solution to the problem, and it's of course very dependent on the country that we're talking about. It's dependent on the type of volcanic activity, whether the volcanoes are more frequent, less frequent, more explosive, less explosive, etc. So yeah, I think it's a matter of building and growing this mutual confidence between hazard scientists and users.
Excellent. Yes. Thanks again, Pablo. We move on